Hello, I'm quickly going to step through how we reverse engineer the format of a flash dump from the Pebble. These sort of reverse engineering efforts apply to almost any sort of data storage and can be used to reverse engineer formats for an app or a new file system data type, an image for example. I'm going to be using a basic hex editor and a binary diff tool. You can get these for pretty much any platform. On Linux I'm going to be using bless and vbindiff to show the binary differences. Okay, let's crack on. These are the things that I'm going to do quickly. First off, I'm going to dump the hex from the device so we can have a look at what's in it. I'm not going to go through the laborious process of that. It will be different for each platform and different app. What I'm going to do is load it into a hex editor. So I'm using Bless. It's the first one I found and it does the job nicely. What I'm going to do is open up the hex of the dump I've just loaded. So this is the file system dump of the external flash on a Pebble. It's got lots of very strange things in here, so what we're going to have to do is have a quick nosy through and see what's in it. First off, I can see we have log, so this looks to be debugging output from the log. What else do we have in here? Oh, lots of blank space here. Oh, and more log stuff. A bit more log. Let's go for a big scroll. I can see the first section of Flash is taken up with what looks to be log output and page data. Now, there was a blob of binary there. What can we see here? So this looks to be a binary application on the external flash. It's probably one of the Pebble system apps. If we keep looking through, we'll find no end of blobs of interesting data. So this one is an ELF binary of some sort. Okay, cool. So once we've had a really good nosy through, we can start to build a picture of what sort of stuff is on here. We know that the Pebble has applications and resources, which are images, fonts, and various other user-defined data. We also now know there is a log section, and presumably there's going to be other kinds of stuff on here like drivers. The system resources will be hiding here somewhere. This looks very much like a system resource here. That'd be a font. We've got a PDC, which is a draw command. So I would say at this hex offset here, or thereabouts, about here, which corresponds to a good offset in the flash, I've got something like the resource table or resource data. Now if I go back up here, actually I think what has happened is I've gone too far. We can go back all the way to 0 times 300,000, and there we have the beginnings of something to reverse engineer. This looks like a table of information, probably a table of offsets for each of the resources on the flash here. What else have we got here? Now I installed a watch face to start with. I use 91dub. So what I'm going to do next is load another one. So fast forwarding very quickly, I've loaded a new watch face, Trek V2, onto the Pebble and dumped the flash to see what happened to the Trek V2 watch face. If we load that in, well, I now have a watch face with 91dub and Trek V2. Again, we have a scan through. Yep, same old log, same old, same old. So you can see here, just loading the two hexes isn't particularly informative. There's not a great deal that you can visually spot between them. So what can we do? Well, we can have a look at the tools. We've got a tool for the job here. It's called vbindiff. You tell it which two binary files you'd like to compare. So I've got 91dub Trek V2 and I'd like to compare it with the base flash, which is just 91 dub. So let's see what this tells us. This application splits the output into two. The top and the bottom are the two different hex files. The red are the differences between them. In this particular app, you just hammer the enter key and it will skip you through. I'm not particularly interested in seeing the differences in logs just yet. It's very not interesting at all. At some point we'll circle back round to logs. So what we're looking for here is just a likely candidate of something that's changed that is significant, interesting, something we can work with. So I may have just skipped past something interesting there. No, there's lots of output from the phone app. What have we got down this end? Lots of very small differences here. Oh, we've got a difference in resource. Okay, let's keep going. Pebble app, 91 dub. Okay, a small difference there. Comset, interesting. Some sort of storage mechanism. Storage 58. Very tedious, I know, but this will become your life for a while. So some more notifications. Oh, what's this? AppDB set. So we've got this whole chunk that's appeared in the top section with Trek v2 called AppDB set that has what looks to be Trek v2 in there. Pixel Miner. So this is a manifest of all of the apps that I've ever loaded onto my watch or are available by the looks of it. And this isn't there in the previous version. Cool. Okay, so we've got an offset. I know that at BAE 000 I've got something called an AppDB set that mentions Trek v2. I'm going to go and have a look for it and see what happens. So there's the same offset, BAE, and we're going to see what Trek AppDB set is and how it relates to Trek v2. So let's find the beginning of the offset. Easy enough, it's here. Something I noticed while I was flicking through, every single Pebble section seems to start with this little magic chunk, and then we start AppDB set, and then off we go with the real data. So the real data itself starts here. Now what we can do with the hex editor is highlight certain hex sequences and it will find corresponding sections. This is good for finding patterns. If I know that this pattern repeats, there's something interesting. What I can also see is the application itself listed. Now what I'm going to do is I'm going to try and line these guys up. There should be, this is close, there should be somewhere where I can get all of these, here we are, all of these to line up, and that is a quick and dirty way of finding how big each section is when we're looking at it. I'm going to infer a few things here. I'm going to infer that we've got something called an application DB, of maybe settings, some information. Maybe it describes the application itself. Maybe it describes where the application is on Flash. That would be really handy at this point. There are a few things that I'm going to look for in this. First thing we need to find out is how big is each of these sections. Where does it start and where does it end? We could quite easily pick a random thing and say, well, that seems like a logical start and end for a section. It may or may not be. Let's see if we can find out where it may start. We've got a couple of FFs here. These normally indicate start and end blocks when you're looking at these things. So let's try and take it from here. We've got the same highlighted bit before, but what we can see is it's lined up nicely. So I'm going to give a good stab and say this here is going to be one, whatever this is inside an application DB. let's assume an application DB is a database, and let's assume each of these apps is a row of data, of structured data of some sort. It makes a lot of sense. So we can start to have a visualization of what the data might look like. The data itself may be very simplistic. We might define the data as app DB sets, and we might say that an app DB set consists of rows of data. App DB row, and that is a row of something. An app DB row. What we can do is say it's an app DB row of type something. We don't know how many rows this contains, this app DB set. There may be hints inside here of how many of these are in this database. It may be a case of we just have to count each one until we get to the end and there's nothing left. So let's assume that it's got a size. So we can start to say that an application has some structure. So now we need to know what each row is and what each of these rows contains, why it's significant, and what we can do with that data. So the basis of reverse engineering this is going to be making quite a few assumptions. We can make some assumptions on what might be in this segment. We might assume that there be some sort of counter, a row index maybe, or an index of the application's ID. There may be things like the app's name. Well, we can see the app's name. So we can already start to build a picture of what this structure is and how it relates. So again, we can create something really simple, like a structure of application databases. So if we were to assume this is some basic structured data, we can call it a struct and give it an outline. First things first, we can see that there's a name knocking around in this data. We can see that it's got an offset. So what I'm going to do now is find out where that sits inside the structure. Its offset is here. It's 52 bytes long. 42 bytes long. The 42 bytes we can break into possibly some chunks in the structure. So what we need are the basis of sizes for each of these segments of data. I don't know what any of these bits of the struct are, so I know that that is 4 bytes, 4 bytes, 4 bytes, 4 bytes, 4 bytes, 4 bytes. Okay, so we have 10 bytes, well we have 10 and a half bytes, 10 and a half words, so at some point we're going to break into a 16. So when all these 4 bytes and 2 bytes are added up, it should add up to 42 total bytes. At which point I'm going to say we have a car of the name of the app. How big is it? We need to work out how big this space is for the application name. So it looks quite big. It starts with www and then has a load of zeroed out bits here. And it goes to the end. So the segment is 96 bytes long. It could be one 96 byte long segment, or maybe the application developers decided to break it into two 32s, which seems like a reasonable assumption in the law of averages. A 32 for the name, 32 for the manufacturer, 32 for some extra stuff, who knows. I don't know this, I'm going to leave it at 96 bytes. Right, so we've got something. We've got a definition of a row, we've got the offset for where the name of the application starts, and we've got an idea of what we need to do with this section. Let's start filling in the gaps. 2B90 FC, presumably if I roll this over, 58. Yep. Okay, so we have 4 bytes in a row, which could be some sort of address. So I'm going to say the first part of this here is an address. Let's give it some notation. It's 2B90 90 FC 58. Well, there's a lot of apps here, and it doesn't seem that this repeats. So why? So let's start looking at why. Well, to C90 FC58. Interesting. And actually, that carries through the rest of the apps here. Oh no, to D90 FC58. So this could be some sort of paging system inside the apps. And here we go, to E. That's quite interesting in itself. Okay, so let's move aside and see what we can do with the next segment. Okay, so we've got no other highlights here. Ooh, okay, we've got a highlight here for 3EC10F. So again, law of averages says it's going to be 4 bytes, and one of these bytes is changing every time. This could be some sort of offset in Flash, or it could be something... yeah, an offset in Flash seems reasonable actually. So, Flash offset? Question mark. So we've got 4 bytes of some interesting... doesn't seem to be incrementing. B5DA. Nope, can't say on that one. Okay, well let's quickly fly on to the next one here. 7E0300. So I see 03 there. 4 bytes again. So the 4th byte here, remember we're little endian, is 7E. 37E, 37F, 380, 381, 382, 383. Okay, we have something here. This is going to be an incremental ID. So I'm going to put this down as an ID that increments. Now something has jogged me here. This number looks very familiar. So 37E in Little Endian. Okay. .380 hex 380. I have seen 380 somewhere. Where did I see it? Let's find out. 37F. So, just by having a good look through this Flash file and finding out what all the areas look like, keeping that a mental map in memory, I recognise these. So, I'm going to hazard a guess then that Pebble app, if I look for this, I'm going to find that it starts with at 0000037F, and the next one is going to be 380. Oh, 376. So we haven't got many Pebble app. Maybe if I get rid of some of this and see if I can find it again. No? Okay. 376. I've got another Pebble app there. These seem to be built-in Pebble apps. So there are a couple of apps on the Flash all ready to go. I've got 91 Dub on there and Trek V2. So Trek V2 37F, which if we remember from the Flash before, Trek V2 was actually, where is it? Trek V2 is the beginning here, 0037F. I now have a good confidence level here that this next section is actually the application's ID. Excellent. Right, so in this database we now have a column that corresponds to the application's ID wherever it's referred to. Nice. Okay, let's keep going. Let's keep going. So the next set of variables are here. Okay, nothing seems to be jumping. No. Okay. Anything common here? Nothing common here. Nothing there. Interesting. Nothing there. Well, there's nothing that jumps out at me straight away on this one. There's an interesting number here that, if we look at this, seems to correspond with something here. Okay, what else have we got? We've got a number 01, 02, 08, 02. So we've got some sort of low number here. Whoa, I can't spell. What else do we have on this? Anything interesting? 0202 0538. Now, I know from experience with working with this device what these numbers actually mean. This is the application's version, and this is the SDK's API, 0538, 0548. You see these knocking around quite a lot while you're working with hex and the application itself. So each of these is 2 bytes. 0201 is the app version, 0513 is the API version. So I'm going to refine the model a little bit here. We have, instead of a 32T, we need 2 16s shimmying for the version number. Okay, so we know that this is the app version, and we know that this is the API version. Okay, now we actually skipped quite a few offsets there, so this is a little bit out of sync. We went wrong here, and it's actually here where these live. Yep, okay. See, what I did wrong there was I don't know what any of this stuff means, and didn't account for it in the flash. So for every 4 bytes that I have no idea what I'm doing, I should have gone over here and skipped an X. But this is now structured correct. So we've got some fields that we still don't know, things that we can infer. I would imagine in this we're going to find the CRC of the application, maybe, which is a numerical verification of the application size, state, etc. We might also find the application size. We found the version, so it does stand to reason that we might find a few other interesting things in there. We might find a few interesting things about where the application is placed on Flash. Certainly we need to go and have a look at these guys. This nicely 2B, 2C, 2D incrementing number has some meaning somewhere. Flash offset, interesting. Application ID, very, very interesting. Where we did look before for the 37E, we can go and find out. It was 37F, I do apologise. We can go and find out if that means anything. So 37F we know that was Trek V2 that we put on here. It also is here in Flash actually. So this is 37F preceded by res. Now I'm pretty sure that if I were to go and look at this here, this would be the resource table, the same as the system resource table we looked at the beginning. And keep scrolling, we've got data again. This is going to be the images, this is going to be the fonts of the application. Nice. So all we need to do now is piece together how the application DB set or the file system table or something defines how these guys ended up in the Flash, where they are, and how we work out how to programmatically manipulate and or interact with those regions. Cheers!